So, as Rob said, we used to be part of Mentor Graphics, and a lot of people don't know that we do vehicle architectures, embedded software, but we're part of the wider Siemens organization. And one of our sister companies, Siemens Mobility, who do the outside the car piece. We're more focused inside the car, which will be the subject of our presentation today. Try this one.
Try here. Aha. So.
Just going to fix this. We're going to talk about a subject which is really important, service-oriented architectures, which are becoming a necessity in today's vehicles. We're going to try and give you a quick briefing on the evolution of vehicle architectures, how they're changing. I'm also going to cover some of the trends which are driving these requirements, and then Brendan will go into more detail on the architecture. He's the real expert. He spent a lot of time in the industry working on these topics. Our solution space has completely changed. We've been providing embedded software into vehicles for nearly 20 years. The Autosar standard has been around since 2003. And of course, the scope has now gone outside of the vehicle, into the cloud, over-the-air software updates. We've got applications both in the cloud and in the vehicle. And as stuff comes into the vehicle, software comes into the vehicle, it needs to go through a secure gateway. It needs to be checked. It needs to be secure. And it's the need for service-oriented architectures in the vehicle has evolved. So we're going to give you a little bit of context on that and how we see the future. The term software-defined vehicle has been talked about a lot. It's very much here. The evolution of vehicle networks, and as Rob already mentioned, around 30% of the vehicle value will soon be software, and most of the innovation is now based around software and electronics. Plenty of industry quotes on that. And one prediction they got wrong in 2014 was the growth of complexity, numbers of lines of code, and number of signals in the vehicle. They way underestimated how much software would end up in the vehicle. So what do we mean by service-oriented architecture? Well, the role of the ECU has changed, the electronic control unit in the vehicle. There used to be dedicated pieces of hardware which did very dedicated functions. In a service-oriented architecture, the ECU can take on different roles. It can change its function in real time. It can provide services, or it can be a consumer of services from other parts of the vehicle network. So if one service provider is overloaded on the vehicle network, another service provider can step in. So those ECUs need very different software platforms inside them. And we're going to talk about how the software has changed inside the ECUs. They also require much faster networks to connect them to each other because there are much larger amounts of data moving around the network. So that gives the need for different networks. And an updated approach to ECU design is needed. And I'm going to talk in a moment about adaptive Autosar, the new standard which is emerging to help SOA. A multi-core ECU supporting multiple operating systems that allows for domain consolidation, as the last speaker spoke about. Nobody wants 150 ECUs in their car. If we can consolidate some of those domains into single units, we're simplifying architecture and reducing the number of components in the car. So the operating systems that go into these ECUs, for many years we've relied on what's called the classic Autosar platform. Autosar, as I said, was introduced in around 2003, very much a global standard now. And it removes some of the vagaries of building an electronic control unit. There are some standard layers, of course, the silicon hardware, the MCAL, and then a software stack which has a few standard components in. And then the application developer develops the code which sits on top of that standard stack. There are a lot of advantages in having that standard. You can interchange ECUs. Tier 1s can, OEMs can source from different Tier 1s supporting the Autosar standard. It can reduce development time once it's established as a methodology. So these advantages have been realized across OEMs, across the whole world. The standard grew out of Europe, but it's really become a global standard. But this wasn't enough to support service-oriented architectures. So an extension to the standard has evolved called Adaptive Autosar. Lots of different building blocks, a lot more flexibility, a lot more programming options, and we'll say a little bit more about that in a moment. In parallel, the networks have evolved, and the previous two speakers have spoken about the different networks. We're now into zonal architectures. Some OEMs are looking at central compute, a single computer in the center of the vehicle carrying a lot of load, but that of course is a high risk in terms of safety. If something breaks, what do you do? But we've certainly moved away from the old domain-based architectures of previous years. And the Autosar standard has evolved to run and evolve alongside the network architectures. As I mentioned, it started in Europe with some of the leading German OEMs, but it's certainly spread globally. And we work with customers of course, in China, Japan, Korea, North America, adapting Autosar standards. The adaptive standard was initiated in 2016. It's in early production with some OEMs, and this is a prerequisite for service-oriented architectures. The previous speaker spoke about safety. There are a lot of questions still on how we safety certify SOA, safety-oriented architectures. When you've got a lot of flexibility and variability, it's very hard to safety certify. So we're going to dive in a little bit more detail now into the network architecture, what's required, what the dependencies are, and I'm going to hand over to Brendan in the interest of time. Those slides are in your pack, but Brendan will take it forward here. Thank you.
Thank you. Okay, so as was mentioned in the sort of introduction, I've got a background working in Tier 1s and OEMs, as well as now for Siemens. So I've been in the sort of bitter end of some of this evolution. For many years, the automotive industry has been adding ECUs. Every time we add a function, we add an ECU. And we've got a constant battle to try and consolidate functions. But as we consolidate functions, there are always more functions, features to be added to the vehicle. So the trend is often upwards. And so we're taking the often functionally oriented buses that we've started to add and turned them into domains, functional domains on the vehicle. As we try and consolidate functions, they start to get pushed into what are now becoming domain controllers as an attempt to actually get this consolidation organized and under control. That's been somewhat enabled by the addition of Automotive Ethernet, which enables to have a backbone. So that cuts the latency down between some of these domains from what it could be, cuts down the gateway loading from a traditional gateway ECU. But the trend is ever upwards. And now we've added this Automotive Ethernet, we've brought in all these possibilities that Ethernet unlocks. The world of IT, the world of VLANs, virtual networks, so we can separate different data traffics on the same physical network and start to have different data streams, allows us to think about the service-oriented architecture. You'll have heard today different people talk about zonal architectures, talk about centralized architectures. I tend to mix the two together somewhat because the direction of travel is similar. Each OEM has a slightly different view about where they're hosting functionality. There are some that really do want to get all the functionality they possibly can in this central compute, have some really powerful central compute. and use the sort of zonal outstations just as I/O concentrators, where they just bring the data together and they're behaving sort of like gateways or switches bringing the data in. Others do want to keep some of the functionality out near where it's happening. But when we move to these zonal architectures, we're actually laying the vehicle architecture out according to the layout of the vehicle rather than the functional domain. So that brings compromise the more you put into the zones, but it's an easier transition. And then, of course, OEMs been OEMs. Some of them do a very gradual transition. Others actually can pause and big bang onto a new vehicle architecture, which is brave, but easier in some ways to make the break with the traditional approach. So if we look a little bit more at some of the opportunities this presents, why it's happening, as ever, the reduction in ECUs is about cost reduction, about weight reduction. And if we can reduce the number of ECUs, and we can do this, use virtual LANs on Ethernet, we can reduce the number of networks. We should be able to make harness weight and cost reductions. We should be able to reduce the number of ECUs. But this means we need these centralized ECUs, the sort of green on my diagram, are more powerful, and you get a cascade of requirements. It's been talked about before by other presenters. More of these ECUs all have functional safety considerations, they have cybersecurity considerations. We're mixing together a lot of functionality, and we need to think about how that's actually going to work. It sounds lovely, but it's complicated to implement. This is both a pro and a con. We're always wanting to cost optimize vehicles, but we have this conflicting requirement that these days we want to, like our smartphones, be able to add functionality over life. We want to software update the vehicles for security fixes, but also to add functionality. That requires headroom on the networks in some of the ECUs. With the traditional approach, which ECUs are we going to update? We can't predict the future. We don't like headroom in all of them because that costs money. So one of the ambitions of a centralized architecture is we can concentrate where we put the overheads, where we allow some capacity into these centralized ECUs. Whether that can be achieved is the next question, but that's the aim. Another trend that's happening sort of in parallel, and has been happening for quite a few years now in some parts of the industry, is the OEMs taking more of an interest in developing more of the vehicle themselves. So drawn here in the sort of greens and blues might be some fairly traditional roles for the development of ECUs and electrical architecture, and the light green might be the tasks traditionally done by OEMs. And the blue tasks would be tier 1s, tier 2s. And the dark green might be where there's been some OEM involvement, some requirements cascaded in. But then I've started to draw some orange lines around some of those boxes where, for quite a few years now, OEMs have been getting more involved in the software side of ECUs, where they might be having specific requirements of their custom comm stacks, or with Autosar more recently. And maybe that means they're getting involved in some application software and doing some integration implementation themselves. And in some OEMs, more and more of them, and in some quite a lot, we see them getting involved in designing ECUs themselves. So they might move on from just specifying a family of microcontroller and some cybersecurity components, through to specifying the full BOM, maybe even designing the PCB layout. And sometimes even getting as far as involved as specifying the MCU themselves or designing it themselves. The best known example is Tesla's sort of self-driving ECU, where that's pretty much all in-house. There's still often outsourced manufacturing, and that's probably not going to change. In part, it's a design responsibility thing. The skill sets are still quite different for manufacturing these from building full vehicles. But that interest in developing the ECUs is there. So I've drawn a selection there with particularly with a startup OEM. You see the make or buy decision has to be made for every ECU, and it can be quite different to a traditional OEM. They don't have the buying power to necessarily get exactly what they want, but if you design it yourself, you can have what you want. So the make or buy decision stretches to different parts of the architecture. With a traditional OEM, you're probably going to focus those in-house ECUs on the ones where you've got some interesting IP, some ideas, something you want to try out that maybe you'll later source commercially in a few years' time once you understand it. So, standards such as Autosar are designed to support the scalability. They are designed to, well, they were originally designed for a traditional model of tier ones and OEMs. But the OEMs have always had some custom requirements. It might be due to history. Diagnostics, they might have a way they do things. Network management, communication, other examples. There'll be some customization that is actually just, I want a specific Autosar version for its function set, specific ASIL capabilities to support ECUs. And Autosar and the Autosar vendors obviously expand to cover off these requirements when they become relevant. But the integration of this software into these ECUs, traditionally a sort of tier one role working with the Autosar vendors, is something the OEMs now have to get more involved in. If they want to do the ECUs, they actually need to understand how to set up the Autosar. They're not just writing requirements where it's got to be my diagnostics and my communications. They actually need to be able to integrate this together. So there's some skill sets that the OEMs either need to reabsorb, refind, that maybe they've lost along the way. There are many tier ones, Vistians, the Delphis, the Magneti Morellis that derived from OEMs were spun out. The world's changed a bit, but those skill sets are now needed in the OEMs again, if they want to do the ECUs in-house. So we've talked a bit about service-oriented architecture and central and zonal architectures, and they somewhat come together, but actually they're not necessarily hard-linked. You can do either, but you don't get the best of them unless you start to do them both. If you do a service-oriented software on a traditional architecture, you can do that between your Ethernet ECUs to a certain extent, but you don't get the full benefits, you don't get the efficiency gains. If you try and apply traditional software to this kind of architecture, you're going to end up with extra ECUs again, you're going to end up with extra connections. It's worth noting that these grey ECUs I've got around the edge of this zonal architecture are still probably, in many cases, going to be Autosar Classic. As we move into these zonal ECUs, I talked about the fact that some of the OEMs really want to put functionality in there, where maybe you start to consider Autosar Adaptive. Some just want to use them as I/O concentrators, and maybe Autosar Classic's okay. It really depends on the philosophy of where the OEM's going with the architecture. Oops. Oh, I didn't mean to do that. One more. The central ECU, though, is where it gets really complicated, where we do have these central ECUs, and sometimes this is in the zonal ECUs, but this is where we start to consider having multiple different softwares. We might have softwares that are better at functional safety, softwares that are better at handling complex image processing, and we may have cores in the silicon that are similarly capable. We might have multiple copies of these ECUs, so I've drawn my multiple boxes for this to be scalable, maybe between a high-line vehicle, low-line vehicle sort of architecture. But those ECUs can have a lot of complexity, and as I think has been hinted at by various people, working out exactly how to implement these is complicated. Now, how far did I go back? So I'm not going to talk to this slide in any great detail, just to say we've been talking about software, we've been talking about zonal architectures. This obviously has an implication all the way through the electrical design, the hardware design of the vehicle. There's a much bigger picture of consequences here. And so some of those teams, some of those skill sets need to evolve as well. And so I'll pass back to Andrew to summarise.
Thank you, Brendan. That was a really fast run-through on Autosar, adaptive Autosar, vehicle architectures. We needed a couple of days to really do it justice, but I hope we've given you a short flavour of what it's about. So the amount of data is increasing. That's normal, it's expected. We're going to need more sophisticated networks and embedded software to handle it. And data travels further on and off board. My first slide, we've got a lot of data outside the vehicle now, we've got a lot of data inside. The two systems need to communicate with each other. Many OEMs have implemented their own over-the-air update strategies. There are some standards governing that. But those over-the-air updates need to be secure, encrypted. They affect bootloaders, they affect gateway ECUs. And these days, we can update during the life of the vehicle. So feature enhancements and additions have become the norm in the current generation of vehicles being designed. We have to be, though, cognizant of cybersecurity. So most OEMs now have a cybersecurity practice starting with WP29, extending that beyond. SOA is developing in parallel. It will allow services inside and outside the car to be available to functions and to the driver and passengers. And we believe it can scale. It can be developed, it can be added to. And Autosar Adaptive will gradually start to appear in non-safety critical ECUs. It won't replace your braking system and your steering systems, but for service functions which are not safety critical, we're already seeing adaptive Autosar being designed in. So we hope this has been an interesting introduction. We do have some adaptive Autosar demonstrations. If anybody wants to see things, come and talk to us. We'll set up some demonstration meetings for you. So thanks everyone for listening. I don't know if we've got time for any questions.